New product announcement from Expedera. Sharad, you can go ahead. Okay, I see you on the screen.
Hi,
Welcome.
Mike. Thank you.
Morning. Good evening for you, I think, right?
No, it's morning.
Okay, great. Sharad is the chief scientist and co-founder at Expedera. He has expertise in AI frameworks and power-aware neural network optimization, programmable data flows. Previously, he was an architect at Cisco, and he'll be introducing the edge AI architecture that Expedera has developed. So welcome. Go ahead and turn on your screen sharing, and I'll talk to you more in the Q&A.
Thank you, Mike. Good morning. Thank you for joining me today. I'm Sharad, chief scientist from Expedera. Expedera is developing high-performance accelerator IP for neural network inference. Expedera was founded in 2018 by a team with deep expertise in building network switch ASICs. My fellow co-founders are Da Chuang, CEO, and Siad Ma, VP of Engineering. Da previously co-founded Memoir System that developed algorithmic memory acceleration IPs. And after acquisition by Cisco, he led data center switch ASIC group. I worked with Da at Memoir Systems and later at Cisco in capacity of software architect. I'm strong proponent of formal methods, hardware software co-development, and programmable data flow architectures. When we started the company, we surveyed customers and available products and quickly realized that advertised stops and thermodynamic dissipation power does say very little about performance and power required for neural network. Current solutions are inefficient and have stalled in performance. And we have specifically addressed this problem by using our networking background to develop a soft IP for neural network acceleration. We are customer proven with tier 1 customer in handheld space. And we have a 7nm silicon proving our IP and software. Today, I would like to share with you our journey on how we approach the problem differently and how that translates into improved performance and efficiency. So when we look at edge AI, we see diverse set of needs. Content capture applications require high resolution processing. Control systems for autonomous and robotics need determinism, both in terms of latency and performance. Edge servers need to process multiple jobs, and consumer devices are concerned about privacy. We also see that real-time models are uniquely designed and they can differ significantly from standard benchmark. But across all these verticals, we see a common trend that everyone wants to do more compute with less power. On this slide, I'm proposing a performance we need for the next generation application, with efficiency demand far higher than existing industry solutions can suffice. Let's take an example of video enhancement. So when a smartphone actually is capturing video at 30 frames per second, the neural networks like CNNs can be used to get crisper details, vibrant colors, and better clarity. Such video enhancement would require 10 to 30 TOPS based on how many stages of quality enhancement is being done under the budget of just 1 watt. We see similar growing demands from autonomous vehicle, low light video, AR, VR, gaming, and super resolution to enable longer battery life and reduce thermal constraints. Clearly, there is a significant effort in the research to develop small footprint neural networks to actually enable these applications. But that's not enough by itself. We also need a hardware which is more powerful and which is more efficient. However, the best of the best solutions in the industry currently reach only 4 TOPS under 1 watt. So when solutions out there are advertising their TOPS, they are mentioning the peak TOPS. The peak TOPS number is a theoretical number that is calculated by frequency multiplied by how many compute units you have on the device. But this does not translate into performance. To understand the performance, we need to also look at what is the neural engine utilization is for a specific workload. Also, when we look at power, it's not just the neural engine power that we need to consider. We also need to consider the system power for overall neural network execution. And this includes runtime, orchestration, and scheduling for the neural engine, as well as the external memory access and system fabric access. Certain architectures also assume model constraints like sparsity or compression or weight clustering. And these can be runtime dependent or very hard to translate from model to model while maintaining the accuracy. And finally, edge systems are very sensitive to cost. And this cost includes the die area as well as the cooling cost and external memory cost. So if peak TOPS is not a meaningful measure, then we still need some measure which can actually incorporate the real world performance with power. We think IPS per watt is a meaningful measure of efficiency. IPS stands for inference per second. One of the important thing to notice here is we need to differentiate between neural engine efficiency by itself and system efficiency overall. The neural engine efficiency includes the power associated with the compute in the neural engine, the memory accesses, SRAM and register file accesses, and the data flow inside the engine. While the system efficiency includes the power associated for external accesses like memory hierarchy, like DRAM access, as well as the runtime overhead of enabling the neural engine. So for rest of the presentation, we are going to focus on ResNet 50 as a benchmark. We know that ResNet 50 does not really represent the real world neural networks, but for comparing the industry solution, that's the only benchmark that is like readily available. So we are going to focus on ResNet 50, 225, 224. And to convert the ResNet 50 IPS per watt into TOPS per watt, we can simply like multiply the inferences per second by 7.8 billion operations, and that would give us like effective TOPS per watt that is being achieved in the industry. So when we look at industry leading solutions, and these includes edge SoC for including GPU and the DLA, the industry leading smartphone SoC and neural network IP provider, we see that like these solutions are hitting a wall around 550 IPS per watt. And this translates into somewhere around like 4 TOPS per watt. But that's not the only thing. The other part of this like puzzle is the system efficiency. So we see that this neural engine efficiency is not readily translated into system efficiency because of the overhead of the runtime, as well as the data flow overhead required to enable this neural engine. So why is that? Why are the solutions are hitting this efficiency wall at 4 TOPS per watt? So when we studied the neural engine acceleration and the overall impact of that has on system power, we noticed that these are the few challenges that must be solved in order to surpass the efficiency wall. And this includes memory sealing. So when a compute needs to be scaled to higher TOPS, the memory storage as well as the bandwidth also need to scale. And that increases the on-chip memory demand. The utilization for compute generally depends on what is the size of the tensor the compute is acting on. And this tensor sizes might not always like adhere to a good like multiple of 64, for example, in case of systolic array. And that's not effectively pipeline-able. When we go from FP16 or floating point implementation in the data center to intake implementations on edge devices, we see that the data flow becomes significant contributor of power as the computational power is reduced to very small part. So minimizing the data flow is very important in order to allow a good system efficiency. Software complexity is another problem. Like we have seen multiple levels of compiler and like multi-layered SDK that gives very incremental benefits and small improvement in performance with significant effort and increases the time to market for the applications. And finally, multi-core scalability. So when a solution needs to scale from single core to multiple core, the scheduling overhead, synchronization overhead, and communication will increase the power consumption and decrease the efficiency of the system. So I mentioned before that we come from a networking background, and when we looked at neural network acceleration, we saw certain similarity in terms of what we want to achieve between the computational domain and networking domain. So for example, the networking switch A6 needs to do routing table lookup with multiple header being deparsed and parsed. And that needs to happen at terabytes per second. So that needs to be guaranteed that every cycle a packet is being routed and a packet lookup is being done. And this is achieved by doing a deep pipeline implementation of this routing table lookup. So there is an underlying theme in network switch A6 that they move a complex software problem into hardware. And we ask ourselves, like, can we do the same thing? Can we actually do the entire neural network decompositions in hardware? Can we actually generate the workload and schedule the workload in hardware? And can we do the resource management in hardware that will allow us to enable very small footprint of memory as well as very small bandwidth and still manage the entire neural network execution with higher efficiency? So what we did is we came up with like a completely new architecture. This architecture has like various building blocks and there is no global interconnect. These building blocks are like laid out in a grid fashion. They include like matrix engine, which can do matrix vector multiplication every cycle. There are vector engines, which can do vector or scalar processing. There are memory elements, there are accumulator, and there is a control block. And because there is no global interconnect, these resources can scale independently, completely independently of each other, as well as they can be modified independently of each other. So this allows us for like a very easy customization. Now the entire architecture is monolithic. That means there is a single control block which controls the entire all the building blocks in this architecture with the single command string, and it sees the entire architecture in an atomic view. And this is like a view that if a command is sent, the command is either complete or not complete. Now to be able to give this like atomic view, the architecture is completely deeply pipelined, which guarantees us one computation every clock cycle. There is no synchronization or there is no back pressure. That means when a control generates a command, that command is guaranteed to be complete, going through memory access, computational block, and result aggregation in deterministic time. This allows us to estimate the performance of not just a single layer, but the entire neural network execution at clock cycle granularity. Another thing to notice is that because of the deeply pipeline nature, the architecture has zero penalty of context switching. So we can visualize this as like the purple execution and the blue execution. Going from purple to blue, there is no penalty or there is no loss of utilization in terms of computation. And this is true even if the size of the purple is changed to n cycle to n+1 cycle. And this gives us the utilization independent of workload. Now imagine having an architecture where we don't have to really like worry about the utilization, and the architectures can have like context switch all at a clock cycle granularity. How would we control this architecture? So when we started with this, we quickly realized that controlling this through software and instruction stream is not really the best in terms of power and performance. To get the full utilization and the full performance out of this architecture, the control system has to understand the neural network, resolve the dependencies in the neural network, generate the work, and schedule the work at a clock cycle granularity. So we have a hardware neural network sequencer which can understand the definition of the neural network, and it can process the entire neural network natively. There is a resource manager which does the just-in-time resource management and allows us to move the data when the data is required and allocate and deallocate the resources. For example, the memories and the buffers in the system whenever the computation needs them and whenever the computation is like done using them. This allows us to guarantee that the engine will require theoretical minimum memory requirement for both on-chip memory uses, as well as the external bandwidth and the data movement. Now, because we have a native execution that the entire neural network execution is being done and understood in the hardware, our software stack looks very simple. So we don't really call it a compilation. It's a preliminary translation from a neural network definition and extracting the metadata and feeding it into the neural network sequencer in the hardware. So from deep learning frameworks, we get like neural network definition as a graph, and that graph, from that graph, we can extract the metadata. The metadata can consist of like input output dimension, it can consist of connectivity, and it can also consist of like specific properties of a layer. For example, convolutions can have stride, padding, dilation, etc. Also, the end-to-end orchestration of the neural network is done in the hardware. That means there is no runtime SOC overhead, and it's a fire and forget architecture that whenever the input is available, we just trigger the neural network sequencer, and it will orchestrate how the weights loads in, how the input loads in, and how the outputs actually goes out, as well as manage the intermediate activations end to end. And whenever the processing is finished, the interrupt is sent to SOC controller that the result is available. So there is really no overhead on the system to enable the neural engine. The architecture scales from 1 TOPS to 100 of TOPS with still being monolithic, which means all the computational engines are still working on a single layer and guarantees lowest latency. It has flexible precisions supporting int8 and int16, as well as floating point 16 and bfloat 16 in case we want to do light training. The architecture is very easy to customize because of the independent blocks, and there is no software overhead. And in the past, we have like we are able to support customer requests like support of bilinear and bicubic in int8 format, which was custom definition coming from customers. We see ourselves applicable across different markets, from handheld devices to edge servers and automotive. And we also see that like compared to the industry leading solutions, we are 4 to 5x better. We achieve 2000 IPS per watt in 7 nanometer in ResNet 50 224 by 224. This translates to 16 TOPS per watt for ResNet 50. Couple of things to notice here is the models are assumed to run unaltered, that they come from TF Lite and they are running as is. That is, there is no sparsity being enforced, and sparsity will further improve the efficiency by approximately 30%. Another thing is when we see this gain in the neural engine efficiency, these gains will also translate into system efficiency. And the difference between system power and neural engine power will be optimal because the end-to-end execution is done natively, and because there is a minimal overhead of the external bandwidth as well as the system fabric access. So these numbers were proven on silicon. We taped out our test chip in Q3 of last year, and we have also been proven by our lead customer, who is tier 1 smartphone supplier. We have measured 18 TOPS per watt on test chip on convolutional networks and are capable of running 2000 IPS per watt for ResNet. If this is the type of performance that you need, we would be happy to evaluate your models and benchmark the performance for you. Please feel free to reach out to me or Nancy, who leads our business development, for more details on our products and offerings. To summarize, we have leveraged the networking principles, which is basically taking a complex software problems and embedding into the hardware, and enable just-in-time resource management, as well as implemented like unified compute pipeline, which allows us to get incredible 18 TOPS per watt efficiency while eliminating the complex software stack and complex compiler. The architecture is configurable and it's flexible. It scales from 1 TOPS to 100 TOPS with deterministic performance and best-in-class TOPS per millimeter square. We are coming out of stealth today. please visit our own website for more details about our product offerings, and please download our white paper. And we'll be waiting for you during our breakout sessions.
Thanks, Sharad. You can go ahead and turn off your screen sharing and we'll do the Q&A.
Thank you.
Yeah, thanks for making your debut at our conference. Again, anybody in the audience has some questions, please go ahead and enter them now in the Q&A box. We had an opportunity to chat before the conference, but I have some more questions. It's interesting that you're saying your lead customer is a tier 1 smartphone vendor. We know that they're all basically already developing their own neural network accelerators. So you must be demonstrating a clear advantage there.
So we see ourselves as like enabling applications for them, which was very hard to achieve with current solutions, especially with the footprint required of like 10 TOPS under 0.5 watts. Mm-hmm. So I don't think I can say more than that, but yeah, so that's
I wasn't prying too much. Yeah. Okay. So again, you're offering IP. Could you say a little bit more then about how you engage with the customers? You said you don't have a traditional compiler model. How do you basically right size your accelerator for their applications?
So I think this is like I'll answer it in two parts. So first of all, because we have a deterministic nature, we can estimate the performance extremely well. It's like we know like every layer how much clock cycles that layer is going to like consume exactly, and this allows us to actually like estimate the performance for the entire neural network. And that engagement model we have with customer, which allows them to decide the trade-offs that are required for on-chip memory and external memory for the area and the power profile. We also work with them understanding their workloads, and basically the idea is to give the best performance for 85% of the workloads that they have. Mm-hmm. And making sure that we cover their use case as efficiently as possible. Sure.
And you described the architecture in terms of the more fine-grained architecture of the MAC arrays, the vector units, and so on. Mm-hmm. Are those fixed, and you go into multiple core configurations, or how do you decide how big the on-chip memory needs to be versus off-chip, and design issues like that?
So I believe this is a very big discussion. We obviously know that there is a trade-off between like having more on-chip memory reduces external memory bandwidth, and one of the way to look at this is you can partition the network. Like based on the on-chip memory you have, you can partition the network, or based on the on-chip memory you have, you can increase the batching that you have, right? So there is obviously a trade-off before we deliver an IP with the customer, and this trade-off is between the performance and the area that the customers can afford to have on the device, right? And in the runtime, there is a trade-off where the algorithms tend to manage what kind of network orchestration can be done. So for example, dynamic batching. So based on what part of the network we are in, we can change the batch sizes. Or for example, just in time, like load of the activation. So our resource manager can transparently load the part of the activations on chip while keeping the part of the activations off chip. So that gives us a like extreme level of flexibility and minimize the bandwidth.
Yeah, it's interesting. So it does sound like it's more flexible than some of the other architectures we've seen. So let's take some of the questions coming from the audience. So I think clearly you're looking for edge devices. There's just a question of the range of applications. You said you potentially can scale to 100 TOPS, but you are looking at edge applications for your IP, right?
Yes. Yeah. I mean, we can scale more than 100 TOPS, but going from 100 TOPS to like, let's say 200 TOPS will require like multiple engine. So we had a customer who asked us to size for 200 TOPS engine where we had to like fit together two engines side by side with still centralized control blocks. So that's still possible. to scale beyond that. But yes, so I think going below 1 TOPS is kind of too small for us, but yes.
Right. Can you tell us some more about that centralized control block? You said there's this one controller that runs the whole network start to finish.
Yeah, so we extract the metadata out of the neural network definition, and that metadata is provided into the hardware neural network sequencer. Now, this metadata is being used to understand what the graph is like, what the connectivity of the graph is like. And by that, we know that which layers can be allowed to execute and how it allowed to execute. And what this native processing allows us to do is basically parallelize different resources. So we have, you can visualize every resource being at its own independent thread and command being generated for these different resources. And as soon as the data dependency is met, these resources can just go in parallel with each other. And this gives us like better flexibility and minimizes the resource requirement like memories and bandwidth.
Okay, and so you only need the one controller. What's the interface to the host processor?
Yeah, we do need only a single controller. It's a controller that scales independent, so that the architecture of controller is independent of what the scale of the IP is, and the interface with the host processor is like so we have experience with like fitting in the standard system fabric buses like AXI or AMBA, and the host interface is simple. It's basically an interrupt or a mailbox that you say that, okay, there are the samples, this is the address of the sample, that the samples are ready. Now we can look at this from like DDR perspective, that samples are in the DDR, but we have like even engaged with customers where the samples are streaming in, and this goes into like how the neural networks are processing the sensor data that has been captured at least amount of power over it. Because if you go to DDR, you do have to like read from DDR again, but if you stream in, then you have a very small memory requirement or power requirement.
Yeah. A question then from the audience. So you talk about the architecture grid array. It does seem that the physical implementation needs to also be coordinated here. How do you control that since you're offering soft IP?
So this is a good question. We do provide physical guidelines. We don't really like harden the blocks, but we do provide physical guidelines which allows the wires to be more straight. And it's an important detail because like this also like increases the efficiency. So the blocks are tiled together in the same fashion physically as well, that like I showed in the architecture, and it is optimized for performance and efficiency.
So it's process technology aware when they get the IP.
Not necessarily, I wouldn't say that, but it's somewhat. I mean,
do you provide synthesis, place and route scripts, or
it's just a guidelines. It's not really. It's not scripts. Yeah.
All right. Question on what is the limitation? I think you mentioned you've been asked to do 200 TOPS. It just seems like you could just do potentially multiple instances of your array.
So after 100 TOPS, it's actually like becomes harder to keep on having a single engine and still meet the utilization for smaller tensors. So we do have to go to multiple engines, but the way the multiple engines are orchestrated with each other is using kind of like a buffered handshake. So as soon as I have the data ready, I can like hand it off to the next engine, and that engine can work on the data while the next batch is being generated, or like, so it's kind of like a streaming protocol.
Got it.
So based on the need, we can scale to much higher TOPS. We do have to discuss the workload though, like what kind of applications do you have in mind? If it's a multiple job application, it's a different configuration, versus if it's like a very huge models that we want to run, it's a different configurations.
Okay, well, we've got more questions I'm going to have time for. Just one quick one. Is the IP available for licensing now?
Yes.
Great. Okay.
Please visit us in our breakout sessions.
We had more in the breakout sessions. Great. Thank you very much, Sharad.
Thank you. Thank you so much.